let's solve the equation e to the 2x minus 2 times e to the x equals 48. Well, this looks messy, but we can rewrite e to the 2x as e to the x quantity to the 2, because this e to the x quantity to the 2 is the same as e to the multiply the exponents x times 2, and x times 2 is the same as 2 times x. So that's what's here. I know we say 2x a lot, but it's really 2 times x. Okay, so this seems rather creative, but the whole point is now we see e to the x in a couple spots, right here and right there. Whereas here we don't. This is e to the 2x. But at least now here there's e to the x quantity to the second minus 2 times e to the x. The whole point is this is a good place to do a substitution. U equals e to the x. The equation becomes u squared minus 2u equals 48. That's a quadratic equation. So even in the original problem, I want you to see a couple steps ahead how what we really have, strategically speaking, is a quadratic equation. And let's subtract 48 on both sides. We hope that this factors, but if it doesn't, we would go back to u squared minus 2 equals 48 and try to complete the square instead. But I think this is going to factor nicely. Yeah, as u minus 8 times u plus 6 equals 0. Okay, now that, again, there's no point factoring until you have a 0 on this side, right? So now that we've got that 0 on one side and we have factors, factors means, factors, each piece here is a factor. So x minus 8 is a factor, u plus 6 is a factor. What we have is u minus 8, that thingy is being multiplied by u plus 6. The result of multiplying two factors together is called a product. And that's, so we have the zero product property. All of the language is very important. It's helpful. It's meant to be helpful. But you've got to use the language yourself for it to be helpful. Otherwise, it just becomes a burden. Okay, u minus 8 equals 0, or u plus 6 equals 0. Don't forget the word or when applying the zero product property. Now we have these tiny little equations to solve, u equals 8 or u equals negative 6. So we added 8 to both sides of the first equation. We subtracted 6 on both sides of the second equation. Now that we've solved for u, right, we've got u by itself here, u equals 8. Now that we solved for u, we've got u by itself, u equals negative 6. This is the time to go replace each u with an e to the x. Right? So e to the x equals 8 or e to the x equals negative 6. So we have these two little equations to solve. Now look, for the first of these, to solve e to the x equals 8, you can get x equals log base e of 8 by applying the definition of logarithm. If you want to write that differently, you could write x equals ln of 8. After all, ln is just a shortcut for writing log base e. So either way, x equals log base e of 8, or you could write x equals ln of 8. So that'll solve the first equation. What about the second equation, e to the x equals negative 6? How do we solve e to the x equals negative 6? Well, there's two approaches. One approach is one that we saw a little while ago, is the equation e to the x equals negative 6 has no solution because the interval 0 to infinity is the range of the function f of x equals e to the x. So the range is talking about the outputs of this function. So e to the x, what value can it take on? The value of e to the x, e to the x would only simplify to be a number that's between 0 and infinity. So how could e to the x ever equal negative 6? It could not. So this equation has no solution. It doesn't matter whether x is positive or negative or 0, whatever you plug in for x, e to the x is always in this interval. E to the x is always bigger than 0, so e to the x is not going to equal negative 6 no matter what you plug in for x. Here's a second way to talk about this, another way to get there. Another way to say that e to the x equals negative 6 has no solution is by applying, as we did here, the definition of logarithm. You'll have x is equal to ln of negative 6. But you can't stop there. You've got to say, wait a minute. ln of negative 6 is undefined because the input to a logarithm must always be bigger than 0. In fact, talking about the domain of the logarithm being 0 to infinity is really the same as talking about the range of the function f of x equals e to the x being 0 to infinity. Because remember, ln of x and e to the x are inverse functions of each other. So the domain of one is the range of the other. Okay, so because of this, we say that e to the x equals negative 6 has no solution. You really got to get there. You got to say that e to the x equals negative 6 has no solution, and the reasoning either needs to be because of the range of this exponential function, e to the x, or because of the domain of the logarithm function. Okay, let's try a more advanced problem. Let's look at log base 3 of 2x plus 5 equals 1 plus log base 3 of 4x minus 1. Now, we had previously on another day seen a question that looked like this and said, oh, we don't have any techniques to solve this kind of equation yet. But now we do. First, let's change the 1. into a log base 3 of 3. Now, we can do that. 1 can be replaced with log base 3 of 3 because, well, log base 3 of 3 equals 1. After all, log base 3 of 3 is the question 3 to okay, there's two 3's here, right? So this 3 to the what equals 3? And, well, that would be 1, right? 3 to the 1 is equal to 3. So why would we do that? Why would we change this 1 into log base 3 of 3? Because now the right side is a sum of logarithms of the same base. That's why we rewrote 1 as log base 3 of 3 instead of writing 1 as log base 4 of 4. Because you have these two logarithms of the same base that are being added together, we can apply the first law of logarithms. So the left side stays the same, but the right side becomes log base 3 of this input 3 times the other input 4x minus 1. Common mistake is to try to do 3 plus 4x minus 1, but that's trying to distribute, or I guess undistribute, or trying to factor logs. You can't factor logs, you can't distribute logs. You've got to use the law of logarithms. Now, we went from a situation where the right side had two logarithms of base 3 to only one logarithm base 3. And this is good because now both the left and the right side of the equation have a single log of base 3 and that's it. Right? There's no more 1 plus business going on. And because we have a single logarithm of the same base on each side, we can now set the inputs to the logarithms equal. So the input of one logarithm was 2x plus 5. The input of the other logarithm was 3 times the quantity 4x minus 1. Now this is a nice equation. Distribute the 3. So you have 2x plus 5 equals 12x minus 3. Subtract 2x on both sides, add 3 to both sides, and you have 8 equals 10x. Divide both sides by 10, and you have 8/10 equals x, or in other words, you have 4/5 equals x. Once you take the fraction 8/10 and you reduce it, you're reducing the fraction 8/10 by canceling a factor of 2 on top and bottom. Remember, in a fraction, the only things you can cancel are factors. Now, because the original equation had logs, we need to go check, is x equals 4/5 a solution? So, first of all, there was a log input. The log had an input here, 2x plus 5. So we'll replace the x with 4/5. And, well, look, 2 times 4/5 plus 5, we don't need to even bother simplifying that any further. All we're trying to do is see if this is positive or not. There's no minus signs there. And if you're just multiplying, adding things that are fractions or not fractions, and there's no minus signs, that should be bigger than 0. The only other original logarithm was 4x minus 1. And so let's replace the x with 4/5 again. Okay, here, because of the minus sign, we do have to work a little further. So 16/5 minus 5/5, well, that's positive. Right, that's 11/5. So that's positive. So, okay, because this value of x caused both of the logarithms that were originally present to have their inputs being positive, x equals 4/5 is a solution, and in fact, it's the only solution because we had discovered no other values of x. So this is a really advanced technique. Okay, what we did here was we turned 1 into log base 3 of 3. Right? This 1 here turned into log base 3 of 3, and we could do that because log base 3 of 3 is equal to 1. And why did we even do that? Why did we turn 1 into log base 3 of 3? It's because when we did that, then log base 3 of 3 plus log base 3 of 4x minus 1, we could apply the laws of logs to it, specifically the first law of logs. And then why did we do that? Because once we applied the law of logarithms, the right side said log base 3 of, all this stuff, but the point is that the equation that would result, this line here, the second line of the answer, there's one log on each side, right? We get an equation with one log on each side of the same base, base 3, with nothing else, right? And nothing else. I want to point out there's nothing, like the original equation here had a single log on each side, but we couldn't answer and nothing else because there was this plus 1. So we had to do something about that plus 1. So this is advanced, right? So this 1 was a problem, and 3 steps ahead maybe, right, is we're going to use this thing of there's a single logarithm on each side of the same base and nothing else. But we had quite a number of things to do to get there. We turned the 1 into a log base 3 of 3, we applied the first law of logarithms, and then we had a single log of the same base on each side. So this is a really advanced technique here. All right, let's try this another question, which is maybe relatively advanced as well. We'll solve log of root x minus 9 equals 2. Now, I said of, even though there were no parentheses drawn. Oftentimes, problems come to us that look like this. But you should yourself, if you want, draw parentheses because, well, really, logarithm is a function. So this is not log times root x minus 9. What would that even mean? Okay, root x minus 9, I know what that is. But to say that one of the pieces in your multiplication is log, what does that mean? That's a function, right? Or you're multiplying a function by an expression? That would make no sense. So, look, this is really log base 10 of, now the parentheses are there, root x minus 9 equals 2. So, I included the base 10. Yeah, this is the base 10 logarithm. When a base is not mentioned, it is assumed to be a base 10. So, look, we've got a logarithm on one side, we've got a constant on the other. Use the definition of logarithm. So 10 to the 2 is equal to root x minus 9. You can swap the two sides of the equation if you want. So root x minus 9 equals 10 to the 2. Let's go ahead and simplify the 10 to the 2. 10 to the 2 means 10 times 10. Right? So make sure that the right side is 100, not 20. 10 to the 2 is different than 10 times 2. So it's important to say this. Say 10 to the 2. So say 10 squared. People want to say things like 10 2, and we'll get in trouble. Now, how do we solve when you have a variable inside a radical? Please remember, square both sides. So x minus 9. So squaring gets rid of the original square root that was on the left side. Squaring the right side, well, 100 squared is 10,000. Now add 9 to both sides, and x is equal to 10,009. We're not done. There are two things to check, in fact. Because the original equation had logs, I mean, not logarithms, plural, I guess, but just had a log, we have to check that the input to each log is positive. Note that the input to the log was root x minus 9, right? The input to the log was root x minus 9, so we need that to be positive. So root x minus 9, plugging in x is 10,009, root 10,009 minus 9. Don't distribute the radical. That would be an error. Radicals don't distribute like this. Okay, root a minus b is not root a minus root b. That's making up things. Simplify inside the radical, and you have root 10,000, which simplifies to 100. And the number 100 is positive, which is good. Yeah, that's good. The input to the logarithm was a positive number. In fact, it was the number 100. But that's not the only thing to check. We actually, at some point, squared both sides. We took an equation, namely this equation, root x minus 9 equals 100, and we squared both sides. And please remember, when you square both sides of an equation, you have to check to see if you got any extraneous solutions or any false solutions. So what are we specifically checking for? Take the value of x and make sure that the original left side is equal to the original right side. Yeah, make sure the original left side, the original equation's left side, is the same number as the original right side. Well, so let's check the right side. The right side was a 2. There's nothing to do, nothing to simplify. The right side's just a 2, already simplified, nothing to plug in. Don't treat the right side as if it's the number 10,009. It's not. We're plugging in 10,009 for each x we encounter. There just happen to be no x's on the right side. So the right side's a 2. Okay. The left side was, just to write it a little differently, was log base 10 of root x minus 9. Plug in the value of x. So here we do plug in x. Right? So we've got log base 10 of root 10,009 minus 9. In other words, log base 10 of root 10,000. In other words, log base 10 of 100. And log base 10 of 100 is, well, 2, right? Because we're answering the question 10 to the what equals 100. Yeah? So, sorry, include this information here for you. Okay? But log base 10 of 100 is equal to 2. So that's good. The right side was a 2. The left side was a 2. So because the left and the right side are both the same number, both 2, this is good. Okay, we checked the other thing we needed to check. We don't have an extraneous solution. We checked both things that needed to be checked. We checked for different things, to be really honest. We checked that root x minus 9 itself was positive, but then we also checked that the original entire left side and the original entire right side end up being the same number because we squared both sides at some point. The conclusion here is that x equals 10,009 is a solution, and in fact it's the only solution.